Hi guys, and welcome to episode 5 of the Rocket Propulsion Masterclass series. This episode will be going over the last sections of chapter 3, more specifically, how the shape of a rocket nozzle can impact its efficiency. So, let's jump right into it, shall we?
3.5, very important. The book comes on to discuss the issues of real nozzles.
Okay.
So we've talked about the sort of divergence losses. Now let's talk about the boundary layer. The problem with a boundary layer, if a fluid is flowing along a surface, then viscosity causes it to have a drag, which tends to drag the surface in the direction of the flow.
Okay, so the exhaust jet is actually pushing the walls of the nozzle downwards as it rubs against
in
them.
the opposite direction to what you want to generate the thrust.
So you're losing a bit of energy there.
Exactly, and in particular, of course, you're generating a force in the wrong direction.
Okay.
So when it comes
the only
to
way to calculate that would be to know the frictional, what's it called, the frictional coefficient of
friction
the
factor,
surface,
yeah.
and like the density of the gas and all of that stuff, which means is there just a table with standard loss values or something?
If you've got, it's quite easy to write a little computer program. The relationships for that have been well known now for the last sort of 100 years. So you take a little bit of the nozzle wall, you work out what the friction drag on that is, and then provided you know the shape of the nozzle, you can simply write yourself an Excel program and put in these little bits of nozzle wall and the forces acting on each little bit, do your summation sign at the end, and then add all those bits up, and that will tell you the friction quite accurately.
And in general, what sort of percentage losses are you usually getting there?
Between 0.5% and 1%.
Okay,
so on the shuttle main engine, for example, roughly 0.6% was actual friction losses along the nozzle wall.
Okay.
Divergence losses usually come to sort of 1.5–2%, something like that.
It's actually very impressive, considering like how much friction must be being applied. But yes.
And then the other source of loss, as I've already said, is that if we did the expansion in a contoured nozzle correctly, we would have no shock losses. But what we're going to do to save the weight of the nozzle is squash it up a bit, and those little bits of entropy now that we've been ignoring might have to take into account.
Right.
And so what we've then got is some shock losses actually within the nozzle, and so friction losses, shock losses, divergence losses, we add all that lot together, and a typical nozzle finishes up at, you get about 97% of the thrust that you calculate using the one-dimensional flow equations.
What's the highest that's ever been on record? Like, what is the most efficient engine we've ever made?
That's a good question. I don't actually know. It's as you go to a much larger nozzle, so for vacuum applications, for example, you sort of say, why can't I have an area ratio of 10,000? Well, the trouble is with an area ratio of 10,000, you've now got a lot of surface area that's being scrubbed by the flow, and as a result of that, the friction losses mount up. Also, an area ratio of 10,000 would be a very long nozzle, so you tend to squash that up a bit more and push up the entropy losses.
10,000, you'd probably get way too much drag. Even in space, you'd get too much drag from the tiny amount of atmosphere up there.
So what you actually find with a real nozzle is that if you vary the area ratio, you're in vacuum, so you're going to have the largest area ratio you can. You actually find that the thrust coefficient is climbing continually as you push up the area ratio, and then finally, because of the friction, it turns over, and there's a maximum area ratio that you can have to give you the optimum thrust. Now, interestingly, if you give 3 different people that problem to solve, they come up with 3 different answers as to exactly what that area ratio is, because everybody's calculation of the friction factor is a little bit different. And you're down into the difference between quite small numbers when you're pushing for that extra little bit of specific impulse. You might only be gaining an extra 1 or 2 meters per second when you're up at those area ratios, so you don't need much change in the friction factor, etc.
Yeah.
So obviously the practical engineer says, enough of that, I'm going to chop it here. And so virtually all nozzles are determined by the ability to pack them into an upper stage.
Yeah.
Sometimes you actually cut the nozzle, withdraw the skirt. So if
you have an extending belt, so section the nozzle.
The RL10 is an example of an engine which actually does that, and there are screw jacks that wind the nozzle extension forward to put it in place.
Okay.
But you've got to be careful, because obviously those screw jacks don't weigh zero.
Yeah.
You have to again do quite detailed studies to actually know that.
And whether or not what size nozzle you want will depend entirely on the vehicle, because there's no point in like getting a nozzle that's 10 kilometers wide if the vehicle only weighs like 10 kilograms, and you're not going to get that much nozzle.
So in any practical rocket engine, it then comes down to packaging issues. If you're trying to make a compact engine, for example, an engine with a single turbo pump and 4 combustion chambers gives you the most sort of compact arrangement.
Right.
It also reduces the weight of the nozzle, because as a single engine with a very large nozzle, the nozzle is a very heavy component.
Right.
And for a length to diameter ratio, so fixed geometry,
Right.
as you shrink the nozzle, make smaller nozzles and more of them, you actually reduce the length of nozzle that you've actually got. You can keep the same area ratio,
right,
but the length of the nozzle will come down if you use more of them, having the same total flow. So one of the examples of where you can see this is SpaceX, for example. SpaceX go for multiple engines, which not only simplifies the development program, but also results in a quite low nozzle mass.
Right.
So if you try to do very large single engines, the nozzle mass actually increases.
Is that because the flow after escaping the nozzle interacts with the flow from the other engines and sort of just?
No, it's a simple geometrical effect. So if I draw
ratios between like
if I draw myself a nozzle of a certain area ratio, and remember it's area ratio that determines the exhaust velocity. Then if I put that in my photocopier and enlarge it, then I've still got the same area ratio, but the nozzle has physically got longer.
Right.
Whereas if I, instead of doing that, I simply put 10 nozzles side by side, then I actually finish up with a lighter nozzle arrangement than I do if I
I understand.
If I just simply enlarge it. So it's just the amount of material that's involved in the nozzle. So we're virtually at the end of this particular chapter. There are a number of examples in here, all of which well worth working through. He puts that together very well, and he does describe in here what the various performance factors are, how important they are, and then finally he talks about the thrust vector alignment. But I won't dwell on that. Thrust vector alignment is quite important because obviously if the thrust is not aligned along the nozzle axis, then that can put a moment on the rocket. The combustion chamber then has to gimbal off axis, and in a real trajectory there are losses due to the fact that the exhaust flow is not going along the axis that the vehicle is accelerating on.
Presumably you can calculate that via just standard cosine loss equations.
Absolutely. So that's very straightforward. So that's chapter 3.
Okay, so we think that's a good place to pause. We're going to stop here and pick it up the exact same place next week. In the meantime, make sure you write all of your questions down in the comment section, and we'll see if we can get around to answering them in future installments. See you next time.